now we're going to start applying all these differentiation rules. So just memorizing product rule and quotient rule and power rule and chain rule really isn't enough. You have to be able to use them. So I feel like this is really a test of your understanding when we start to apply. And the first thing we're going to do is we're going to use implicit differentiation. All right, so let me give you an example of what an explicit function is. An explicit function is basically where we have y defined in terms of x. So y can be alone. So one example would be if you just had y equals x squared minus 5x plus 7. And this is how we're used to seeing functions. Okay, we work with these functions very easily. Another example would be in terms of f of x, where we have the independent variable separate from the dependent variable. All right, so here's my dependent variable is f of x, and then I would have the square root of x squared plus 5. Okay, these are explicit functions. Now, implicit functions where we cannot separate x and y completely. Y will never be completely in terms of x. So one example, just a polynomial style function would be if you had y cubed plus y squared minus x squared equals like -4 or some constant. Okay, no matter what you do here, you're not going to be able to have y alone and everything in terms of x on the other side. All right, but it's still a relationship. So it's not necessarily a function, okay, in terms of passing the vertical line test, but it does have a relationship, all right? Another example, polynomial style, would be x squared plus xy minus y squared equals 3. Okay, just kind of a mixture of these xy variables. And then let's go ahead and throw a trig one in here. If you have cosine of x and sine of y is equal to the square root of 3 over 4, x and y are not independent of each other. All right, so we would have to really work with these. So we've got our x and y variables all kind of blended together. So what we use this process in a lot of different things, and that's kind of why we're going over this process. We're going to apply this to other things. But a lot of times we use it with respect to different variables. So we're going to work through this example. We're going to differentiate with respect to t. All right, now this doesn't make a lot of sense to you yet. As we work through it, it will. But usually we do stuff with respect to time, so we use t a lot whenever applying this particular process. Okay, so we're going to use the chain rule for every single derivative that we take. But each derivative is going to have a derivative of its variable, okay, with respect to t as part of the derivative. So let me show you that example. And we would take the derivative of y cubed, which would be 3y squared. But now we want to take the derivative of whatever variable I was working with. So that's where the dy dt, because I am taking the derivative of y here with respect to t. Then I would add 2y, and again, because I took the derivative of y, I would say dy dt. Everything is a chain rule because we're treating the inside of the function as this variable. All right, that's the idea. All right, and then we would have minus 2x, so it's just a power rule, and then we would have dx dt. Now, you don't have to have these parentheses, but I do feel like sometimes it helps. I should have put parentheses on that first one, especially while this process is new. But the parentheses themselves are not required. It just might help you clarify some things. All right, and then the derivative of -4 is 0, and I have no letter associated with this -4, so I'm not going to put any letter here anyway, but it would just be 0 times that. All right, so I'm going to leave that as 0. This is a derivative found implicitly. Okay, so dy dx or dy dt is not by itself. I've got all of the variables kind of mixed up. Okay, so same situation for part B, only now it's asking me to do it with respect to w. So we use w a lot of times for width. Sometimes we're asking to find a rate of change with respect to a width changing. So it would be the same process where we would do 3y squared dy dw. And yes, it matters. Okay, if we tell you to take the derivative with respect to a specific thing, okay, you have to make sure that you have that variable there. So this again would be dy dw. This would be minus 2x dx dw equals 0 again. So it's the same equation, but now my derivatives are different because this is with respect to w or whatever the application situation could be, and this is with respect to time. Now, like I said, this is going to make more sense when we apply it, so don't get too bogged down in it just yet. but you do need to recognize how we use this, okay? All right, so let's do one more. And this is most likely how you're going to see most of your practice right now. And then we'll kind of branch out into the dy/dt and dy/dw kind of stuff a little bit later. So now we're going to do it with respect to x. So what does that look like if I have an x in the equation? Well, I've got 3y squared dy dx. So remember, this is the notation for the derivative of y with respect to x. This is what we've been finding, is dy dx. Okay, plus 2y dy dx minus 2x. But now I'm taking the derivative of the x variable with respect to x. So I always write this out because I want you to see my process, but that is equal to 1. So that does disappear in a way. It simplifies down, right? So if I were to rewrite this and make sure it was as simple as possible, I would write it as 3y squared dy dx plus 2y dy dx minus 2x equals 0. Okay, I would not have that dx in my simplification. Okay, so just be aware of that. That's an important part of this process. Okay, so now we're going to use algebra to solve for dy dx. dy dx again represents the derivative with respect to x. Okay, so x is going to be the variable that is the independent variable, okay, and the change in y depends on the change in x. That's what this is referring to. All right, so the change in x is what I am evaluating, and so hopefully the more we work with this, the easier it'll be. All right, so let's do this. If I have 3y squared plus 2y, oops, sorry, I did not put my dy dx there. 3y squared dy dx plus 2y dy dx minus 2x equals 0. I want to solve for dy dx. Okay, now this is going to test your algebra skills, this whole process. So if you are weak on your algebra, I expect to see you in tutorials regularly. All right, if you're strong in your algebra, hopefully the process will make sense. I'm trying to get this by itself. Well, I have 2 of them. So that means I need everything that has a dy dx on one side and everything that doesn't on the other side, because what I'm going to end up doing is factoring this out. So now I'm going to take the dy dx out, and I'm going to have 3y squared plus 2y. Now, mathematically, if I add 2x to both sides, I'm going to get equals 2x. So in order to solve for dy dx by itself, I would then have to divide by 3y squared plus 2y. And I would do that on both sides. You do not have to show me every single itty-bitty step, but I do need to be able to see your process. So then I would just rewrite, just to clean things up a little bit, dy dx is equal to 2x over 3y squared plus 2y. And so yeah, it's a little bit messy, but ultimately what this represents is at some point, okay, this equation will give me the slope of any point on this particular function. Okay, so on this function or on this relationship, okay, I can use this to find the slope at any xy point. And that's what we're trying to find. So yeah, it's a little bit messy, all right, but it will still give me a numeric analysis of the slope. Okay, so it's not going to be any messier than if we plugged it into just a regular power rule. We would take this, we would plug in an x, we would plug in a y, and we would find a numerical value for my slope.